Hello everybody and welcome back to another episode of Coronavirus Calculus. Well, anyway, today we're actually talking about an important section in the textbook, 1.2, Finding Limits Graphically and Numerically. So we haven't actually talked about limits yet, but there are three main ways of figuring out what these limits are, and we're going to be talking about two of them in this section today. So first, what is a limit anyway? I don't know, I had to Google it, that's what my teacher always says, but I can't watch a video of this because I'm making the video. So let's get into it. Unlike the last section, section 1.2 is really where calculus starts. You could skip over 1.1 and not really be missing much, but 1.2 is where things really start coming in hard. First, let's talk about the concept of a limit. So a limit is basically an operator in a way. You write it as lim like this, and then you put your function right here. And as you guys know, a function, f of x, is basically a fancy way of saying y. Like y equals x or whatever. F of x equals x. You put that function right here, and you put a certain value here, like let's say x goes to 3. I'll give a quick example. Let's say f of x equals x cubed plus 4. And then we'll draw the graph really quick just for context. Go up 4 right here. And then it's going to look a little bit like this. You guys have seen what this graph looks like. But let's say we wanted to evaluate a limit right here at x equals 2. We would write that as limit x goes to 2 of our function, which is x cubed plus 4. Make sure if you have things that are added together in your function that you put parentheses around it, because this statement right here is not the same thing as this statement that I'm about to write right here without the parentheses. This statement right here is saying that you're evaluating the limit at x goes to 2 of the function x cubed plus 4. But here you're saying the limit as x goes to 2 of this entire thing. In this case, I believe it'll come out to be the same value because that's how constants at the end work. But if you were doing something more complex, that was maybe a polynomial with more than one x degree in it, then that would start to come into play. Let's see here. That is how you write a limit, but now let's explain what a limit is. A limit is basically the value of a function, or the estimated value of a function in a way, as you approach a certain value on the graph. So let's go over two ways that we can find out what this limit is. The first way is called numerical, finding limits numerically, So let's rewrite our problem right here. Limit x goes to 2 of x cubed plus 4. Make sure to put those parentheses once again. And then numerically, solving limits basically means you're making a table. And in this table, you're going to have a set of x values and then a set of outputs from your function. Basically, you're putting in the x and checking to see what the f of x is. You'll put the x value you're finding your limit at in the middle of the table. Sorry, I'm going to make it a little bit longer. Right about there. And then you want to pick values that are really close to your limit right there at 2, but not exactly there. So let's say we pick 2.01, 2.1 there. And then over here we go 1.99, 1.9. And basically we're trying to find out what this value is right here, what the function approaches, by looking at what's happening around it with the function's values. So let's compute these things really quick and figure out what our values are going to be. So let's see here. If we're going to plug in 1.9 here, we would just say in our graphing calculator, or whatever calculator you have, 1.9 cubed plus 4. So then what you're going to end up getting here is about 10.859. Now let's try the same thing with 1.99. Let's see here. You're going to get about 11.881. Let's look at it from the other side. Now if we put in 2.01, you're going to get 12.12, 12.121. And then if you put in 2.1, you're going to get 13.261. Optimally, you would want to have another set even closer right here, like 2.001 and 1.999. But just for the purposes of time, I'm not going to waste your time with that, because we can see here, these values are getting bigger and getting closer to a certain value. And here the values are getting smaller, getting closer to a certain value. And you can tell that that is going to be 12 in this case. 11.81, extremely close to 12. 12.121, close to 12 as well. If we were going to put those extra values in there, it would become even more clear. One special thing about limits, let's say that we had a function that had a hole there. The function did not have a value at 2. The value of the limit does not change, because the value that the function approaches as you get closer and closer and closer to 2 is still 12. This value in the middle does not matter. We don't care about this one. We care about what it's approaching. The thing that separates a limit from the actual value of a function is that the limit does not care if there's something there or not. The function does, but the limit does not. If you're evaluating a limit here, you can evaluate, excuse me, that was rude of that pen. You can evaluate that limit there no matter if there's a hole or not. There are some more properties of limits that we'll get to in a second, but that's one of the main takeaways from this lesson, is that limits are you approaching a value, but you never actually get there. You're like getting to that 1.999, 1.99999, and that 2.001, 2.0001. That's all that we care about. We don't actually care about this in the middle. That's just what we're looking at as a reference. So that is evaluating limits numerically, which basically just means a table. But graphically, I'm sure you can tell what they're saying with that. I'm going to erase this. Evaluating a limit graphically is very simple. You graph it, and you look at what the function is approaching. So if we graph our little thing here, use the same function again. Looks something like that, pretty close. You'll put a 2 here, 1, 2, and then 4 up. Not to scale, I'm sorry, but that's just kind of how it goes with these rough sketches sometimes. And I'll just be extra and write f of x equals x cubed plus 4. because I can, to label that line. So then what we're really doing here is looking for where the limit is at x equals 2. So we're looking at what the function is doing on the left side and the right side of x equals 2. So we can see that from the left side, it's getting closer and closer and closer to 8. From the, oh wait, my bad. I meant to say 12. Excuse me. If you had this on a graphing calculator, it would be a lot more clear, but I'm doing this from memory. So you're approaching, getting it closer and closer and closer from the left, it's going to approach 12. You approach from the right, it's getting smaller and smaller and smaller, getting closer and closer and closer to 12 as you approach x equals 2. So what we can say as a conclusion from either of these processes is that the limit as x goes to 2 of x cubed plus 4 in the parentheses is equal to 12. And this is a true statement. There's another way to figure out what limits are, which is known as the analytical process, evaluating limits analytically, but we're not going to get to that in this section. We'll get to that in the next part. So I want to talk about some more processes of limits, or not processes, excuse me, properties of limits before we finish up here today. There's still a few more things that are important. I'm going to write the basic format of a limit just so you guys can see that and write it down. Limit as x goes to c of f of x. You might see this thing also called L. L just stands for limit. Limit as x goes to c of f of x. This c right here is going to be a constant. A constant is just a number, like 2, -2, 7, 0, whatever. You might also see some infinities or negative infinities as well, but we're not going to get to that for a while because that's a completely different ball game that we're not going to play with right now. So let's do another example, shall we? If we have a function that looks like this, let's see. Let's have a parabola. Wait, excuse me. Let's have a line. Except right here there's a hole. And let's say that that's at 3, 3, 3. This is going to be y equals x minus 3 times x over x minus 3. So what this would actually be is x squared minus 3x over x minus 3 as our function right there. So, what if I asked you to find the limit as x goes to 3 of y, which is the same thing as f of x, just using a different notation to make things click, I guess. What would you do? So the first thing you could do is look at it numerically with a table, but we don't want to do that, that's too much effort. So let's look at it graphically and see what we can figure out. So we can identify that right here, y of 3, which you can write the same as f of 3, it's that kind of thing. Y evaluated at x equals 3 does not exist. There's no value there. Like, it's undefined. There's a hole in the graph. If you were going to plug it into the function right over here, you would get 3 squared, which is 9, minus 3 times 3, which is also 9, over 3 minus 3. This is a dirty, dirty thing right here. This 0 over 0. 0 over 0 is not something that we can deal with at this point. Just know that anything over 0 is not going to exist. And 0 over 0 especially is a very dangerous thing. We can't just say that y equals 0 over 0 or something like that. There's another step that we have to do to be able to find things like that. But we're not going to deal with 0 over 0 right now. What we are going to do is approach from both sides to see what's going on. So from the left side over here, as we're getting closer and closer to 3, it looks like the function is also getting closer and closer to 3 as a y value. If we look at the right side, as x is getting closer and closer to 3, y is also getting closer and closer to 3 because it's decreasing towards 3. So we can say that the limit as x goes to 3 of y is 0. Or why did I say 0 and write 3? I'm such a numbskull right now, but it's 3. That's one example of, like I said before, if there's a hole, there can still be a limit there anyway. Let's go through another example really quick. Now I'm going to introduce the concept of one-sided limits. Let's see here. Let's do a nice little function here. Okay, so you may be saying, hey, I've never seen a function like this before, but that doesn't really matter when we're talking about finding limits graphically and analytically. Let's just say that this is f of x. I know the equation to it, but we're not going to complicate things with that right now. So as you can see, if I was going to ask you to find the limit as x goes to 0 of f of x, we could just use the same things that we've been doing. We could look at it numerically. All the values over here are -1, -1, -1, -1, everywhere over here. So on this side, we would be approaching -1. Okay, so the limit's -1. But if we look at the other side, it's all 1, 1, 1, 1, 1, +1. That's an issue. Because over here, the function's telling us we're approaching 1, but over here, the function's telling us we're approaching -1. That's an issue, because they conflict with each other. So mathematicians have come up with a way to write this. You can do just left-hand or just right-hand limits. A right-hand limit is written like this. Limit as x goes to c, and then you do a little plus sign, a small like superscript plus sign above that of f of x. And this is going to be a right-hand limit. If you probably know what's going to happen, but if you write the limit as x goes to c with a negative subscript or superscript like that, that's a minus sign by the way, of f of x, then that's going to be a left-handed limit. So let's evaluate the left and right-hand limits since we don't know how to do the main one right now. So first, let's say, what is the limit as x goes to 0 from the left of f of x? So now we're just taking into account the left-hand points. Let's see what it's approaching. So it's staying at -1, -1, -1, -1. So it looks like it's approaching -1. So we can say that the left-hand limit of x goes to 0 from the left is going to to be equal to -1. Let's do the same thing from the right. If we did limit as x goes to 0 from the right of f of x, we would get 1. By the same logic, as we're approaching from this side, it's just 1, 1, 1, 1, 1. And as I said before, we don't care what's actually there, we just care about what it's approaching. Okay, so these two statements are true, but what do we say for our original problem? There's no clear answer. Is it 1? Is it -1? Is it both? The answer is neither. Whenever the right and left-handed limits do not match up, you have to say limit as x goes to 0 of f of x does not exist. That's what this DNE stands for, does not exist. Because if you have two different values you're approaching, there's no singular limit that's going to connect what those two values are. It's not approaching a single value, it's approaching two different values from two different sides, and we can't have that, so we just throw it out. DNE does not exist. So that's a takeaway from this. If the limit as x goes to c from the left of f of x is not equal to the limit as x goes to c from the right of f of x, limit as x goes to c of f of x overall does not exist. That's a very important concept that you need to get, because that's going to be showing up everywhere in the future. Okay, let's see here. Okay. Now let's talk about something a little bit different. Another type of problem having to do with limits. What if I drew something really quick? What if I drew the graph of f of x is equal to 1 over x squared? That's going to look like this. Going to have one like that. One like this. Okay. So what if I told you to find the limit as x goes to 0 of f of x? Well, if we look at it from the left and right, let's start from the left. This thing has an asymptote here. It's just blowing up, getting bigger and bigger and bigger. Kind of like it's never ending. It's just going to keep getting bigger, larger and larger and larger into infinity. So there's no like singular value that the limit approaches. Same thing from the right side. As you approach from the right, it's getting bigger and bigger and bigger and bigger. No matter what number you find there, there's always going to be a bigger one and a bigger one. So we could say that it's approaching infinity, but at this point, we're just going to say that since the limit does not approach a specific value, a specific real number, infinity is more of a concept. It's not really a number. It's not really a number that can be output from an equation. So we're going to say, once again, that this limit does not exist, because there is no finite value that the limit is approaching. Okay, there's one more really quick concept that I want to go over. Let's see here. What happens if you have a function like this? Let me see. Okay, sorry, I had to look at the book really quick because this is such a rare function for me. I almost never draw it ever, only really for this. So let's say there's a function that like oscillates like this, and the oscillations are getting closer and closer together. Eventually to the point where you can't even see them because they're getting so close together. They're just infinitely getting smaller like that. And then the opposite is true on the other side. You have something that looks like this, and then you have these things that are oscillating, getting closer and closer together, closer and closer. So if you have something like this, this is kind of a rare thing to see, but this is called a function that is oscillating with increasing rapidity. And as I said, this is not a thing that shows up very often, so I wouldn't stress about this. But if you have something that is just getting more and more and more compressed as an oscillation, one example would be y equals sine of 1 over x. That oscillates with increasing rapidity as you approach 0. There's no limit in this case either. So we would say limit as x goes to 0 of sine 1 over x does not exist. Because if you have something that's oscillating more and more and more to the point where you can't even pin down what it is, and in this case, if you plug in 0 here, you'd get sine of 1 over 0, and that doesn't really make any sense. So you would not be able to figure out what that is. That's like asking what's the sine of infinity, when you really can't do something like that, because sine is a function that'll just keep oscillating forever. And if you pick a big number, you can always pick an even bigger number to figure out where sine is. So sine does not have a limit like that. Let's see here. That's about it, I think, for limits. There's not a whole lot left. But just to finish things off, we could do one more limit, just to test some knowledge. So, if I had a random function like this, I don't care what it is. It could be this, for all I care. It just needs to have a whole, and then we'll put the actual functional value up here. Let's say this is negative 4, and let's say that this is 2, and let's say that this is 10. This is our f of x right here. Let's say f of negative 4 is equal to 10, because that is the actual functional value at that closed dot. Open dot represents a whole. So the function is defined everywhere on its domain, domain meaning just the x values. If you plug in an x value to this function, you will get a value out no matter what. But the function isn't continuous. There's like a hole here with a displaced point up here floating off in the void. But we can still find a limit, right? So let's say the limit as x goes to negative 4 of f of x. And if we were asking what that was, how would we do it? Well, just off the top of your head, it may be tempting to just say that the answer is 10, because that's the functional value. But based on what we've talked about today, that would be wrong, because you need to look at the behavior of the function around the point that you're looking at, rather than the actual functional value, which is here. Examiners are going to try and trick you by putting this like point up here, and it's like nana nana boo boo, I'm here to screw you over because I'm going to make you think the limit is actually here. But no, it's actually here, because the functional value is what we care about right there. The functional value as it approaches, not the functional value at the actual point. So from the left we're approaching 2, from the right we're approaching 2. It does not matter that the actual functional value is 10. Our answer is 2. So now you know the basic idea of limits. You know what limits are. Those people in pre-calculus that are like, haha, You don't know what a limit is, do you? You're such a loser. Well, now you do. Like, I can definitely empathize with being that kid who was told what a limit was in pre-calculus by my friend. But now you know what it is. And it's not all that crazy. You just have to look at what's happening around your point that you're looking at. In this case, x equals -4. But in other cases, it could be almost anything. So that's a quick introduction to limits. Next time, we're going to be talking about the elusive third way of finding limits. Finding limits analytically, which is my favorite approach because these guys kind of here are pretty tedious. If I had to rank them, I would say analytic is my favorite, and then graphically, and then numerically. Numerically is just cumbersome. You're not going to see me drawing tables out here every day. But anyway, thanks for watching. We'll go into 1.3 next time. See you guys then.